Hello, welcome to online lecture series on first order partial differential equations. So let me recall the definition of Lagrange's linear partial differential equation. A general form of Lagrange's linear partial differential equation is of the form P into P plus Q into Q is equals to R. A partial differential equation of first order is said to be in linear if the degree of the first order derivatives P and Q is 1 and P, Q and the dependent variable Z are not multiplied. So to find the general solution of this Lagrange's linear equation, whose general solution is of the form phi of u comma v is equal to 0, where u and v are two independent solutions of this equation, we consider the auxiliary equations or subsidiary equations. What are auxiliary equations? Dx by t is equal to dy by q is equal to dz by r. Now either by grouping the terms in the auxiliary equation or by using the multipliers, we find two independent solutions u and v to write the general solution. So here in this lecture, we find the general solution of some first order partial differential equations. So this example is find the general solution of the PDE y plus zx into p minus x plus yz into q is equals to x square minus y square. Now the given PDE is of the form p into capital P plus q into capital Q is equals to r, where capital P is y plus zx, capital Q is minus of x plus yz and r is x square minus y square. So we write the auxiliary equations for this PDE. The auxiliary equations are what are auxiliary equations? Dx by p, that is dx by y plus zx is equal to dy by q, that is dy by minus of x plus yz is equals to dz by r is x square minus y square. So these are auxiliary equations for the given PD. Now from this auxiliary equation we have to obtain two independent solutions either by grouping or by using multipliers. So first let us check whether we can group any of the two terms and obtain at least one solution. If not, we go for multipliers. See, can we group any of the two terms and directly integrate to find the solution? I think there is no such possibility here because there are the terms cannot be cancelled and variables cannot be separated to integrate. So we search for multipliers. So think about the multipliers for this auxiliary equations. First set of multipliers. Choose the multipliers L, M and N. See here we have x square minus y square here. So if we multiply this with y, we get y square xyz. And if we multiply this with x, we get minus x square minus xyz. And if we add all the three, plus x square minus y square plus x square plus xyz and minus xyz cancel. So that L into P plus M into Q plus N into R becomes 0. So this may work out. So we take L is equals to y, M is equals to x and N is equals to 1 and check whether LP plus MQ plus NR is 0 or not. Now find out LP plus MQ plus NR. What is LP plus MQ plus NR? Y into y plus zx minus x into x plus yz plus x square minus y square. 1 into x square minus y square. That gives y square plus xyz minus x square minus xyz plus x square minus y square. So if we see here plus y square minus y square plus xyz minus xyz minus x square plus x square gets cancelled and we have 0 here. Therefore LP plus MQ plus NR is equals to 0. So when LP plus MQ plus NR is 0, what can we write? L dx plus M dy plus N dz is 0. Therefore L dx plus M dy plus N dz is equal to 0, which gives L is y, so y dx plus m is x, x dy plus n is 1. So dz is equal to 0. Now if you look at the first two terms, it is y into derivative of x plus x into derivative of y. Y into derivative of x plus x into derivative of y is derivative of xy. So you can write this as derivative of xy plus dz is equals to 0. Now upon integrating both sides, we get integral of derivative, because both are inverse operations, they get cancelled and we have xy plus integral of 1 dz gives z is equals to c1. This is the first solution. U of x comma y comma z is equal to c1 with the set of multipliers. L is y, m is x and n is 1. Y comma x comma 1. Now for the second solution, we have to search for another set of multipliers. So I will write the first solution here. Xy plus z is equals to c1 is the first solution. Now we try for another set of solutions. Now we try for second set of multipliers. These are the auxiliary equations. First set of multipliers are y, x1. From that we obtained a solution. Xy plus z is equals to c1. Now what can we take the other set of multipliers as? Suppose if we multiply this with x and this with y, m is y and n is, let us see what we take n. M xy plus x square z minus xy plus y square z, x square z. If we multiply with minus z, let us see what happens. Let us check for this set of multipliers. Now consider LP plus MQ plus NR, that is equal to x into y plus zx plus m is y and q is minus of y into x plus yz, n is minus z into x square minus y square, which is equal to xy plus x squared z minus xy minus y squared z minus x squared z plus y squared z plus xy minus xy plus x squared z minus x squared z minus y squared z and plus y squared z cancels and we get 0. Therefore LP plus MQ plus NR is 0, so that we get L dx plus M dy plus N dz is equals to 0. Now what is L dx? X dx plus y dy minus n is minus z dz is equals to 0. Now we can directly integrate because x terms are with dx, y terms are with dy and z terms are with dz. So if we integrate this, integrating this, we get integral of x is x square by 2, integral of y dy is y square by 2 minus integral of z is z square by 2 is equals to c2, or x square plus y square minus z square is equals to 2c2. This is the second solution which is independent of the first solution. First solution is xy plus z is equal to c1. This is x square plus y square minus z square is equal to c2. That is u of xyz is c1. This is v of xyz is equals to c2. Therefore, the general solution is phi of u comma v is equal to 0. That is phi of xy plus z comma x square plus y square minus z square is equals to 0. This is the general solution of the given PDE with the two set of multipliers y x1 and another set is xy minus z. Then let us see another example. Solve the PDE y square plus z square into p minus xy into q plus zx is equal to 0. As you can see here, it is a linear partial differential equation because the degree of p and q is 1. And let us write the given equation in the Lagrange's form of PDE. The given PDE can be written as y square plus z square into p minus xy into q is equals to minus zx, which is of the form p into capital P plus q into capital Q is equals to r, where p is equal to y square plus z square, the quotient of dou z by dou x, q is equals to minus xy, and r is equals to minus zx. Now consider the auxiliary equations. The auxiliary equations are dx by p, that is y square plus z square, is equal to dy by q, that is minus xy, is equals to dz by r is minus zx. Now see whether you can group any of the two terms and directly integrate and obtain the solution. So if you consider these two terms here, x can be cancelled and we remain with dy by y is equal to dz by z, which can be directly integrated and obtain the solution. So we consider 2 and 3 terms. So consider dy by minus xy is equals to dz by minus zx. Cancel x along with minus sign. Then we have dy by y is equals to dz by z. So that all the y terms are towards left hand side and z terms are towards right hand side. We can integrate now. Integrating we get integral of 1 by y. Integral of 1 by y is log y is equal to integral of 1 by z is log z, and because these two are logarithmic terms, even the constant also I take it as logarithmic term, arbitrary constant as log c1. Log y minus log z is equal to log c1. Log y minus log z can be written as log of y by z is equals to log c1, or y by z is equals to c1. This is the first solution. Here we did not consider any multipliers, but we grouped these two terms and upon integrating we obtain the solution. Y by z is equals to c1. So I write the first solution here. Now we try for the second one. So these are the auxiliary equations we have here. These are the auxiliary equations. Again I write it here. Dx by y square plus z square is equal to dy by minus xy is equals to dz by minus zx. These are the auxiliary equations. Now I think we cannot group any other two terms. If 2 and 3 are grouped and we obtain the solution. And we cannot group any other two terms, so we will try for multipliers. What multipliers can we take here? So think once. You can try different options. Here maybe if we multiply this with x, we get xy square plus xz square, and if we multiply this with y minus xy square, and this with z we get z square x, so that we get cancelled. So I choose L is equals to x, M is equals to y, and N is equals to z, and let us check whether LP plus MQ plus NR is equals to 0 or not. What is LP plus MQ plus NR? X into P, that is xy square plus xz square, plus M into Q gives minus xy square, N into R minus z square x. xy square minus xy square plus xz square minus xz square cancels and this gives 0. Therefore, LP plus MQ plus NR is 0. This implies L into dx plus M into dy plus N into dz is equal to 0. That means x dx plus y dy plus and z dz is 0. So that we can integrate and find the solution. Integral of x is x square by 2. Integral of y dy is y square by 2 plus z square by 2. Integral of z dz is z square by 2 is equal to c2, or x square plus y square plus z square is equals to 2c2 or any other constant. So we obtain two independent solutions. One is y by z is equal to c1. Another one is x square plus y square plus z square is equal to 2c2. Therefore, now we can write the general solution. The general solution is given by phi of u comma v. That is phi of y by z comma v is x square plus y square plus z square is equals to 0. So one obtained using method of grouping and the other solution using method of multipliers, where the multipliers here are taken as x comma y comma z. So here this is another example. Solve the PDE. Y minus z by yz into p plus z minus x by zx into q is equals to x minus y by xy. This is directly in the general form of Lagrange's linear equation. So we can consider the auxiliary equations. What is capital P here? Y minus z by yz. Capital Q is z minus x by zx, and R is x minus y by xy. So if we take the auxiliary equations are dx by y minus z by yz is equal to dy by z minus x by zx is equal to dz by x minus y by xy. So to find the multipliers, first let us simplify this and write this as dx by y minus z by yz is 1 by z minus 1 by y is equal to dy by z minus x by zx is 1 by x minus 1 by z is equal to dz by, and this can be written as 1 by y minus 1 by x. Now it will be easy for us to find the multipliers. So what multipliers can we take here? It is very simple. You have 1 by z minus 1 by z minus 1 by y plus 1 by y, 1 by x minus 1 by x. So if we take multipliers as 1, 1, 1, we get one solution. So let us choose L is equals to M is equals to N is equals to 1. Then LP plus MQ plus NR is 0, because 1 into this plus 1 into this plus 1 into this, all the terms get cancelled and we get 0. So if LP plus MQ plus NR is 0, then L into dx plus M into dy plus N into dz is equal to 0. That means dx plus dy plus dz is equal to 0. Now integrating both sides. On integrating, we get integral of 1 dx is x, integral of 1 dy is y, integral of 1 dz is z is equal to c1. So x plus y plus z is equals to c1 is one solution when we take the multipliers as L1, M1 and N1. Now we have to search for another set of multipliers for the second solution, which is independent of the first one. So how do you find another set of multipliers? Say if we multiply this term with x, say we choose L is equals to x, M is equals to y and N is equals to z, then let us see what happens to LP plus MQ plus NR. LP plus MQ plus NR gives x by z minus x by y mq, that is y by x minus y by z plus z by y. No, you are not getting this. Z by y minus z by x. So terms are not getting cancelled. So we cannot make LP plus MQ plus NR is equals to 0. So we have to choose another set of multipliers here. So let me take L is equals to 1 by x, M is equals to 1 by y, and N is equals to 1 by z. So that LP plus MQ plus NR now gives, see, 1 by x, that means y minus z by xyz. M is 1 by y, that is z minus x by xyz, plus N is 1 by z, therefore x minus y by xyz. We take xyz LCM, then we get y minus z plus z minus x plus x minus y. Minus y plus y minus z plus z minus x plus x, which gives 0. Therefore LP plus MQ plus NR is 0 here. So that L into dx is equal to 0. Therefore L into dx plus M into dy plus N into dz is equals to 0. That means 1 by x dx plus 1 by y dy plus 1 by z dz is equal to 0. Now integrating, upon integration we get integral of 1 by x is log x plus integral of 1 by y is log y plus integral of 1 by z is log z is equals to log c2. That means log a plus log b plus log c is log a into b into c. That is log of x y z is equals to log c2, or x y z is equals to c2. This is second solution with the multipliers 1 by x, 1 by y and 1 by z. Whereas first solution is x plus y plus z is equals to c1. Therefore the general solution is given by phi of x plus y plus z comma xyz is equals to 0. Thank you for watching this video. Keep practicing. Thank you.